So, as we take a look at graphing something like 3 to the x now instead of a 2 to the x, I want to first talk about like parent function, because when we were doing all those 2 to the power of x ones, I was talking about parent function being 2 to the x. In this kind of a case, when we talk about what the parent function is, it's going to be a 3 to the power of x. It's no longer 2 to the power of x. Whatever the base is, that is, whatever number is raised to the power of x, that's the one that's part of our parent function. Now, that means that there's not actually any transformations in this equation. So you'll notice it's a different equation, but there's still no transformations. Now, that tells us that the general shape is going to be the same, but a few details of numbers are going to change a little bit. Now, the first thing we have to know then is the asymptote. Remember before, when we were graphing 2 to the power of x, it had the asymptote at 0. And so we'd always put the asymptote at 0. In this case, with no transformations, it's still at 0. And so our asymptote's going to be at y equals 0. So the first thing I need you to do on your graph then is draw a dotted line in here at y equals 0. Now that we've drawn in our asymptote, now it's time to put in our first point. Now, when we were graphing 2 to the power of x, remember our first point was always up 1. Always putting our first point up there. In this case, that's not changing. We're still going to put our first point up 1. Now, why is that? Because 2 to the power of 0 equaled 1. That's why we always started up 1 with that one. 3 to the power of 0 is also 1. In fact, anything to the power of 0 equals 1. All right, so we know the first point's up at 1. From there, this one's a 3 to the x. When it was 2 to the x, remember that meant that I doubled my height. So I'd like go from 1 to 2 to 4, because I was doubling my heights. In this case, though, it wouldn't make sense to double them. I'm multiplying each time I go over by another 3. And so, you might already be thinking that maybe we'd triple the height. Yeah. And yes, in fact, that is what we would do. We're going to triple our height. And so, our first point was up 1. Our next point is up 3, because I'm doing the 1 times 3 to get 3. My next point after that, I'm taking that last height that I just found of 3, and I'm going to do 3 times 3, which equals 9. So I go up 1, then I go up 3, then I go up 9. Now, of course, that's all that's going to fit on this particular graphing grid. But what if we did want to do one more? I just want to make sure that you're seeing the pattern and how it's all working. I would take that 9 that I just went up, and I'd multiply that one by 3. And so it would be up 27. Now, that's definitely way off our graphing grid, but that's where it would end up. And if I was making an insanely large graph, I'd multiply that by 3, and I'd go up 81 the next time, and so on and so forth. We're always multiplying our heights by 3 as I go to the right. Well, if I'm multiplying by 3 as I go to the right, what do you suppose I'm going to be doing as I go to the left? Yep, we're going to be dividing by 3. And so as I go to the left, I'm dividing each height by 3. Now, of course, remember, we're getting as close as we possibly can here. It's not like on your paper that you can just zoom in. That'd be awfully convenient if you could, but we can't. So you're just being as close as you can to actually getting it right at a third. And then a third of that, and so on. If it's not perfect, that's okay. Just be as close as you can to actually drawing in those thirds. Once you've drawn in a couple points on each side, then you can go ahead and draw your graph. And so notice, by changing the base, really all we're doing is just changing the pattern, so that instead of multiplying and dividing by 2 to get our next point, we're multiplying and dividing by 3 to get our next points. Now, if we can graph something like 2 to the power of x or 3 to the power of x, it also means we can graph something like 1/2 to the x. So write this down above your next graphing grid. All right, so for some of you, the 1/2 might scare you, but it's okay. We're going to be able to deal with this just fine, as you'll see. We just got to actually construct it. Now, first of all, the 1/2. Does that mean we've done any transformations here? No. That is still our parent function. Because anytime we just have a number to the power of x, that's our parent. Now, that means no transformations, and that means that our asymptote is here at 0 still. So I'm not moving the asymptote at all. First thing you're doing on your graph then is you're drawing in the dotted line there at 0, making sure that it's clear that you actually did draw it in. Again, I'm trying to build a habit in you here of always drawing in the asymptote, because by seeing it there, you're reminded that you're going to have to do it when you move it as well. All right, now the first point. Well, remember earlier we talked about 2 to the power of 0 equaled 1. 3 to the power of 0 equaled 1. What do you suppose 1/2 to the power of 0 is going to equal? 1. Because anything to the power of 0 is 1. Hence, when x is 0, y is 1. So I plot my first point up 1. Now, from here, when it was, and I'm looking to see what I'm doing as I go to the right, when it was 2 to the power of x, I multiplied the heights by 2. When it was 3 to the power of x, I multiplied the heights by 3. When it's 1/2 to the power of x, what do you suppose I'm going to be multiplying by as I go to the right? Yeah, I'm multiplying by 1/2. Now, for some of you, that's less comfortable to think about it as multiplying by 1/2. So if you want to, multiplying by 1/2 is the same as dividing it by 2, right? So if you want to think of it as dividing by 2, that's fine. But that's what we're doing to the right now. Each height, as we go to the right, will be half as high. And so, once again, you're just getting as close as you can on each of those points to actually making it go half as high as our last one. So you notice I started up here at a height of 1. And then my next one's at 1/2. And then my next one, I'm going to say it's half of that. Technically, that's at 1/4. And you only really have to give me 2 of these points. But the more you draw in, the smoother your graph will look. So if you then want to cut that in half, you can. If you want to cut that in half, you can. They, of course, get closer and closer to our asymptote. And, of course, in this case, that's meaning closer and closer to the x-axis. Now, once we've plotted those, then we need to go left. Now, as I'm going to the right, remember I said you could think of this as just dividing by 2. Well, if I'm going to go to the left then, what can I think about doing? Yep, multiplying by 2. And so as I go to the left then, I'm taking my first point that I plotted up there at 1, and I'm going to double my heights. And so as I go to the left then, it goes up 1 at the start, and then up 2, up 4, up 8. It would then go up 16 if we could actually fit it on the grid, but of course we can't fit the 16 on the grid, and so on. Now, in case you're curious, why is it multiplying by 2 over there? Well, remember when it was like 3 to the power of x, we were dividing by 3. Technically what we're doing is we're dividing by 1/2. But if you remember our rules for dividing by a fraction, multiplying by 1/2 is the same as dividing by 1/2 is the same as multiplying by its reciprocal. Multiplying by 2 over 1, of course, is just multiplying by 2. And of course, once you've plotted your, go ahead and draw your curve in that goes through those. Now you'll notice a relationship between this graph and 2 to the x. You should be feeling like these are pretty similar. 2 to the x, remember, looked roughly like this, if I can get it looking somewhat reasonable to the way it looked. Basically, it's kind of like it's been flipped over the y-axis. Now, it's not technically a transformation like that, like it's been reflected, but it does look the same as what that would have caused. Because in that case, we're multiplying by 2 on the right side and dividing by 2 on the left side. And in this one, of course, dividing by 2 on the right side, multiplying by 2 on the left. So we're doing the same things. Now that we've done those, we can tackle something that's got a little bit more going on in it. So we got y equals 1/3 to the power of x minus 2. Write this, of course, above your next graphing grid. All right, and I always want to think about these questions down the left-hand side. Now, do you have to write them down every single time? No, you certainly can, and it's a great reminder about why it works the way it does. But if you aren't writing it down, you at least should be thinking about the answers to each of these 3 questions over here. So like the parent function, that's whatever is raised to the power of x. So this is going to be the 1/3 to the power of x for my parent function. Now, the nice thing about knowing what the parent function is, first of all, you know that our graph is going to look exactly the same as that would, just it's going to be changed ever so slightly. You'll notice what's outside of my parent function. I have that minus 2 hanging out there. Now, the minus 2 is hanging out at the end of my equation. Which way does that move it then? Up, down, left, or right? Down. Yep. This one is going to be shifted down 2. Now, if it is shifted down 2, where is my asymptote going to be? Well, my asymptote's normally at 0, right? If I move that down 2, does my asymptote move as well? Yes, it does move as well. It specifically moves to actually negative 2. My asymptote is negative 2 now. Now, on your graph, start by drawing in this dotted line for your asymptote. If you leave off the asymptote, usually we end up miscounting something along the way and it gives us some headaches. Take a little bit of time up front. It saves you time in the long run. All right, now for my first point. It's really about the first point. If you can plot the first point, everything else follows just from the parent function. So, what's 1/3 to the power of 0?
1.
1. And so this one also is going to start up 1. Now, when I say up 1, though, I mean up 1 from what? The asymptote, exactly. That's partly why we draw in that asymptote, is we're trying to remember everything is now relative to that asymptote. I don't care about where the x-axis is here once I've drawn in that asymptote. The only thing that matters is where the asymptote is, because that's what I go up 1 from. And as I go to the right now, what am I going to do to the heights of my points? So as I go to the right here, I'm multiplying by 1/3, or dividing by 3. Either way, of course, it means the same thing. Now, when I say going down by that amount, when I say it's going to be 1/3 as much, remember, that is taking this distance, the original distance of my point, and that's what I'm going to take 1/3 of. And so my next point is going to be 1/3 of that height from the asymptote. Again, the importance of having drawn in the asymptote there and saying that's what everything is relative to.
Why is it going down on that side?
So it's 1/3 as high to get to this first point after that. And then going from that point to my next one, it has to be 1/3 as high. Because every time we go to the right, I'm always multiplying by this number, whatever's to the power of x. That's what I'm multiplying by as I go to the right. Now, as I go to the right, I'm dividing by 3. So what am I going to be doing as I go to the left? Yep, we're multiplying by 3. So as we go to the left, I'm going to multiply by 3. So, again, this first point, it's up 1. So my next point then has to be up a total of 3. And then the next point after that is going to have to be up a total of 9. Because I'm always multiplying whatever the last height was by 3 as I go to the left on this one. And now that I've plotted all the points I can fit on there, remember at least a couple of the fraction ones, go ahead and draw your curve that goes through it. And again, you'll notice, since it's a 1/3, just like when it was 1/2, it's up high on the left side, and it's getting really small on the right side. It's decreasing over the x value. Sometimes we'll actually call this formally exponential decay, because we're getting less and less of it over time. We're now going to go back and graph this. This will be the last one that we do together today. Back to whole numbers, because we've got to be able to do it both ways. All right, so first up, parent function. Remember, the parent function is just the number raised to the power of x. In this case, the number is the 4, and so that's going to be to the power of x. So that is my parent part. The minus 7 is not part of the parent then. The minus 7 is moving it. Whenever you add or subtract, it's moving it. Now, which way does a minus 7 that's up in the exponent move it?
To the right.
Yep. This one's going to move it to the right. Now, how do I know it's to the right? Well, first of all, the minus 7 is with the x. So it's up with the x. So that tells me already that it's going to be moving it in the x direction. And then whenever we move it in the x direction, minus always goes right, Plus always goes left. One last detail. My asymptote then is normally at 0. If I move that asymptote to the right 7, did it really move? Not really. No, it's a horizontal line. It didn't move up or down at all, so it's still at 0. And so once again, on your graph, make that the first thing that you draw in there. Draw in your asymptote, please, here at y equals 0. All right, so from there, our first point. What's anything to the power of 0? 1. But where that 1 is no longer on the y-axis. Now, how do we know that? Remember, normally it would be starting right here, up 1 on the y-axis. But because it shifted right 7, I take that point and I move it right 7. That's how we get that first point. Now that I know the first point, I can mentally, if not physically, check off that transformation. I used the fact that this thing is shifted right 7 because I now know where it starts. From there, all I have to do is know that my parent function is 4 to the power of x. Because I know my first point, and therefore I know that I need to multiply the height of that point by 4. And so, of course, 1 times 4 is going to give me 4. So my first point is going to be up 4. How high would my next point need to be after that then? Well, it'd be 4, the 4 that I have there, times 4, which, yes, is 16. Now, that's off my graphic grid. So actually on the right-hand, I'm only going to be able to fit this one point. On the left side, as I head to the left, what am I doing to the heights? We're dividing by 4 now. Or you could also think of it as 1/4 as high. That's the same thing. So again, this first point's up 1. The next point over will have to be up 1/4 of that. So that's getting pretty small pretty quick. And then the next one after that will be up 1/4 as high as that. Get real small real quick. But please give me at least 2 of the fractions. All right, and then once you plot those points, of course, go ahead and draw your curve through. One note on the curve. Take a look at the curve you drew in and look at the top right side. Now, remember, if I went over to this x value, my point would be up here somewhere at 16. It's going to be way up there. So when you draw in your curve, you're drawing that smooth curve through those points. Don't have it cross that next grid line like that. You know it doesn't cross that line until it gets all the way up to 16. So just kind of visualize, okay, it's going to be going up there, and extend it to the edge of the graphing grid. Always extend it to the edge of the graphing grid. And then kind of eyeball where you're targeting off in space there.